I'm Angie Rizzi, and I'm from NASA Langley Research Center, and I'm here today to share with you one of my favorite activities, which is an aerosol catcher. So in order to do this activity, you need a few supplies, but they're simple. So you want some clear contact paper, you need a piece of cardboard, and as long as it's as big as a regular piece of paper, it's fine. You don't have to have a specific size. You're going to want to have the two sheets from the globe activity, the one which is the sample grid, and then the student activity sheet, which we'll be using a little bit.
If you don't have a printout of the sample grid or the student activity sheet, you're welcome to draw your own. It helps to have a ruler, and you can use blank paper or lined paper or graph paper.
You need some scissors to cut your contact paper, some tape, something to write with, and a number cube or dice. Okay? So we want to do this activity to try to catch some of the aerosols, which are particles that float in the air. Some aerosols are big enough for us to see with our eyes or maybe with a magnifying glass, but some are too small for us to see. So for this activity, we're only going to be able to look at aerosols that we can see with our eyes or with the magnifying glass. So what we need to do is cut a piece of contact paper. Now I've already cut some here, and you just want to make sure that it is big enough to cover that grid. Okay, as long as it's big enough to cover the grid, it's going to be a good size, but not bigger than the whole piece of paper. Okay, then I'm going to take my piece of cardboard, and I am going to take the contact paper, and notice I did not take the back off of the paper yet, and I'm going to put the back side facing up, and I'm going to tape down the corners. And I only want to tape the corners. I don't want to tape all around all the edges. I just want to tape the corners so it will stay on the paper. But that's not sticky. To make it sticky, I have to peel the back off. And when I'm doing that, I'm going to have to get it started. And I try not to put my fingers on the sticky part. So I try to keep my fingers on the corners. And when I get close to one, I will put my finger down and go by. And it's okay to leave a little bit of paper under a little bit of the back under the contact, under the tape, sorry. So here we go. I'm gonna peel some more. I always like peeling the paper off, it's kind of fun. Notice I'm really trying not to get my fingers all over the sticky paper. Doing the best I can, and little corner here, holding on. Come down here and do these last two corners. Okay, so this is what I did. I now have the four corners. It's okay to have the back under them, and this is ready to put down and see if it can catch some aerosols. Well, you want to leave it for at least 2 hours and maybe even longer. So a couple things you can do to make this into an experiment is you could make more than one, and you can put them in different places, or you can leave them for a shorter amount of time and a longer amount of time, or something like that. Now, once it's done, and because we don't have 2 hours to wait, I already did this, and I already did 2, and I've already finished them up. Okay, so we're going to use those in a minute. But let me show you what we'll do after we left it for a couple hours. So pretend that you left it there, and here's my sheet, and here's my sample grid. And I am going to lay the sample grid down on top of the sheet, making sure that the grid is over the sticky part. Okay, I'll stick it to there, And now I will take the contact paper off, and this is why I only wanted to tape down the corners because it would be too hard to take it off otherwise. And now the sticky side isn't up. But we can go and we have all these squares and we can count how many might be in each square. Okay? So this is where we're going to now be able to use our student activity sheet. Now on the student activity sheet, you can record all kinds of things about what it was like that day, and you can check off the boxes. And I'm going to show you how to fill in this table. And this is where the die is going to come in. So if you notice here on the grid, we have the numbers from 1 to 6 going up on one side, and then on the bottom they go from 1 to 6. So you roll your number cube. I rolled a 2, so I go down, I go up to the 2, then roll it again, 3, and I go over 3. Okay? I will look at this square now with my magnifying glass, and I will see how many aerosols were in there. So if I use the one that I left out for a long time earlier, I have 2 aerosols in that square, okay? And you do that 10 times with 10 different squares. So if you roll the same square, then you don't want to do that one again. And after you do that, I took this one and I did 10 squares and I put how many, and I had found 27 aerosols altogether on this collection sheet. And then I found the average by dividing my total of 27 by 10. And so on average, there were 2.7 aerosols that I could see per square on my collection sheet. So I hope you have fun doing this, and please share with us if you do this activity.
Now let's hear from a scientist about what you might find in your sampler.
Hello, this is Ali Omar from the Langley Research Center. Today I'm just going to talk about different sizes, because what can we see and what can we not see. Aerosols that are very small, smaller than 2.5 microns, that is 2.5 millionths of a meter. Those are the aerosols that we measure for air quality and health because they affect our health. Those aerosols we cannot see with our eyes, but most of the other larger aerosols, especially things like dust and sea salt. These two types of aerosols are natural aerosols. They occur naturally. Usually the sizes are large enough, anywhere from 2 microns to 300 microns, and so we can see them. The other very small aerosols that we cannot see are usually formed in the atmosphere. For example, when you drive down the road, your car emits exhaust. This exhaust is transformed in the atmosphere from a gas to a particle, and these particles are usually very small, much smaller than 1 micron, and so we cannot see those. Sometimes they will combine, they will nucleate and aggregate, and so you get many particles coming together and sticking together, and then you can see them by looking at them with your bare eyes or with a microscope. So the type of aerosol usually depends on the size of the aerosols. Usually depends on how they are formed. Aerosols that are formed by in the atmosphere, they were emitted as a gas and they are formed in the atmosphere, are usually very small. Aerosols that are emitted directly into the atmosphere are much larger. So what you collect on your experiment and you can see with your eyes most likely are dust that was generated directly as a particle and then was suspended in the air and then was settled onto your experimental sheet of paper, and you can see it.
Hi, I'm Joe Atkinson, and I am at the hangar here at NASA's Langley Research Center in Hampton, Virginia, this historic facility where Gemini and Apollo astronauts trained to do rendezvous docking maneuvers and where we keep our fleet of research aircraft will be home base for Activate scientists and crew when they begin conducting research flights out over the nearby and super conveniently located Atlantic Ocean just next month. I'm joined today by Luke Ziemba. He is the instrument scientist here at Langley for Activate. Behind us, you can see the Falcon and King Air aircraft that they will be using. When I look back at the Falcon, it has all these crazy probes and sciencey looking things sticking out of the top of it. What are we looking at? What do these things do?
So for Activate, we're making lots of different measurements, so we need lots of different probes and instruments in the aircraft. If we look at the crown of the aircraft, you can see 4 inlets. On the left side, as you're looking at the aircraft, is a gas inlet that we use to bring in air and measure the concentrations of CO, CO2, and methane in the atmosphere. Next over is an aerosol inlet that we measure the properties of particles in the atmosphere, so the optical, chemical, and microphysical properties of aerosols. Next over is what we call a CVI, or counterflow virtual impactor, and that rejects those aerosol particles, and we only look at droplets that enter the probe, and then we evaporate those droplets and look at their composition. And then lastly, we have a cloud water collector, and that collects droplets inside the clouds, brings them into the aircraft through tubes, and then we collect water samples in vials that we take back to the laboratory and look at post-mission.
We have some instruments on the wings here as well. Can you tell us what those do?
The wing probes measure the cloud properties. On the right wing, we have what we call a cloud aerosol precipitation spectrometer, or CAPS, and that measures the size of the droplets and the number concentration of them. On the left wing is a similar probe that's operated by DLR, and that probe measures the number concentration and size of droplets, but over a different range of particle sizes.
Oh wow, so we're getting onto the Falcon here, and man, I can see that it's pretty crowded, and you don't even have everything on here yet, right? So tell me a little bit about what it's gonna be like.
That's right, so we're currently integrating the Falcon, meaning we're putting our instruments on. We currently have 3 racks on the plane, and we're gonna have 3 more sitting essentially right where we are on the plane now.
And you have to have people on the plane too.
Right, so during flights we're going to have 2 pilots up front, but we're also going to have 2 scientific operators that will sit in front of racks and monitor instruments and keep them calibrated.
What does the Falcon do during these flights?
So we're based out of Hampton, based here at home, but we're going to be flying out over the ocean. So we can do local flights out over the ocean, or we can go to Bermuda and back, or target different cloud environments. Our flights are about 4 hours in duration, and we fly from about 500 feet above the water surface up to about 5,000 feet. And we're porpoising between those altitudes constantly.
While you're doing that, the King Air is going to be flying too. So talk to me a little bit about what the King Air is going to be doing.
Right, so the uniqueness of Activate is that we have coordinated flights between 2 aircraft. So we're flying low, but the King Air is flying up at 9 kilometers, looking down on the scene with remote sensors, and especially with the new system that we have, a drop-on system.
You actually have a drop-on here in your hands. Can you kind of explain to us what we're looking at here?
Sure. The drop-on has a parachute on one end and it has sensors on the other. We measure temperature, pressure, relative humidity, and wind direction and speed with the sonde. We use a launcher from the aircraft, and it drops at about 11 meters per second, and we get a sounding of the atmosphere as it falls.
You have 2 other instruments on the King Air. What are they?
A research scanning polarimeter and a HSRL, or high spectral resolution LiDAR on board. Those 2 instruments in conjunction allow us to retrieve the properties that we're measuring on the Falcon aircraft.
We don't actually have them to show you here, but we are going to take you to the lab to see the HSRL.
This is our instrument and how it's configured on the aircraft. This is a high spectral resolution LiDAR. So what we do is we send different color pulses of laser light out into the atmosphere from the bottom half of the instrument. Those laser pulses go into the atmosphere, and we collect that scattered light energy from the atmosphere with our telescope, and then direct that light into the various detectors in the instrument head. At the operator station, I can look at those various signals coming from all the detectors, getting information about the aerosols and clouds. Now, why that's important, you've already heard about the detailed measurements that the Falcon is taking as they're flying down low. Well, we're flying up high, and we're measuring, it's a remote sensor, so we're measuring from the aircraft all the way down to the surface. And we can combine those measurements from both aircraft to really get detailed information and dig into the science of how aerosols and clouds interact.